Hello, welcome to another lesson. This is still page 6 from the last lesson that we had. And we're going to continue to simplify radicals pretty much for the rest of the unit. In this first section, we're going to be just simplifying straight up. The next few sections are going to be adding and subtracting, multiplying and dividing, and then kind of just a few more special simplification questions. And then at the end of this, we'll do some practice problems. So I don't know how much we're going to get through in this video, but we'll see how things go and work from there. So we've already seen this page. Basically, the key points that I want you to point out are know what the perfect squares are, which is, for example, 1 squared gives 1, 2 squared gives 4, 3 squared gives 9, 4 squared, 5 squared, 6 squared. What would all those things give us? Those are the perfect squares. Perfect cubes the same way. 1 cubed, 2 cubed, 3 cubed, 4 cubed. Perfect fourths. 1 to the power 4, 2 to the power 4. 3 to the power 4. This is what I'm trying to get at here with these perfect fourths and fifths and so on. Those are things that are going to be very important going forward, okay, especially for this section. So we're asked here to simplify the following expressions. Let's start with root 72. It's a root. It doesn't tell us what the root is, but we've seen before that if it doesn't give you a number as an index, it's assumed to be a square root. And what we're going to do, we need to think about the perfect squares, okay? So perfect squares are 1, 4, 9, 16, 25, 36, and so on. Those are all the numbers squared, 1 squared, 2 squared, 3 squared, and so on. Try to find the biggest perfect square that fits into 72. Or in other words, if we take 72 divided by something from this list, will we be able to get a perfect square out of this? And I guess it's just easier to show. The square root of 72 is the same thing as saying 36 times 2. And I picked 36 because it's a perfect square and it's a factor of 72. 36 times 2 gives us back 72. And the very nice thing about this is if I get the square root of both of these now, square root of 36, square root of 2. This is something that we can do with the square roots. You're allowed to split them into two separate multiplications. We know what the square root of 36 is because it's 6 squared. Long story short, square root of 36 is 6 because it's a perfect square, and we're left with 6 root 2. So sometimes, and I'll show you kind of an alternate way to do this, many times I would like to skip the step. The first step is the same. You have 36 and 2 under the radical. But what I think of it like is 36 is our perfect square, okay? It's over here. Think of it as bringing it outside of the radical and square rooting it along the way. So I'll just rewrite this. Give myself a little more space. And one way you can think of it is you've got a square here. Just bring it out, square root it, and now it's gone. It's a 6 outside of a root 2. Or in other words, we get the exact same answer as we started with, or the exact same answer that we got in question A, okay? So with variables, it's a little different. I'll do more variable work in a second, but let's do one more example where we just have numbers. So third root. See, the index is a 3. So what this means, really, is that we have perfect what? Well, perfect cubes. We've got to be thinking about our perfect cubes. What numbers, when multiplied by themselves, in a total of 3 times, give us back these numbers? So 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, or 3 cubed is 27. Where am I getting these numbers from? Well, you can actually steal them from above the page. You can use these as your reference. 1, 8, 27, 64, 125. And you can just pop those out on a calculator if you want. And ask yourself, which one of those perfect cubes, if any, fit into 40 as a factor? And you should see without too much effort, you can do it with 8. 40 divided by 8. 40 divided by 8 gives us 5. So really it's 8 times 5. So to say it's the cube root of 40 is the exact same thing as saying it's the cube root of 8 times 5. 8, just like before, okay? 8 is a perfect cube. We can bring it outside, get its cube root, and we'll have our answer. Okay, what's the cube root of 8? Put it in on your calculator if you need to. What's the cube root of 8? It's 2. There's no nice cube root of 5, so this is the final answer here. Let me show you how to get this on the Casio and the TI-84. Getting cube roots on the Casio is quite simple. You can see the root button above it as a shift is the cube root. Put in 8 to get the cube root of 8. Another way to get it is to know what it means to be an index. An index is just a power, where the number of the index is on bottom, right, of a fraction. So you have 8 to the power of 1 over 3 is another way to write this. It gives us 2, or 8 to the power of 1 over 3, if you want to see it visually. It's the exact same thing. Everything's going to give you 2. There is, I think, maybe 1 over way. No, that's about everything for the for the Casio. For the TI-84, or TI-83 or similar, I think it all works the same way. The safest way is just to take 8, and your power button's over here. Some of you don't know that. 8 to the power of, and it's 1 over 3, right? 8 to the power of 1 over 3. If your calculator doesn't look exactly like this, it'll look close enough. You might just have the symbol, the up symbol, the caret symbol, and you'll put bracket 1 over 3, close bracket, and you'll get the same thing. Either way, play around with that until you get a 2. Another way to get it is to hit math, where you can do a bit of math, and your cube root should be right there as 4. So math 4 is a cube root, and you can put an 8 in there, and again we get our 2. Now you might wonder, what if it's not a 3? What if it's a power of 4 or 5, like the index is 4 or 5? Well, you can still do the exponent thing to the power of 1 over 5, 1 over 4, something like that. Or under this calculator anyway, if you hit math 5, it's going to be something to the power of the root, or sorry, something root, which means is it a power of 5 or an index of 5? What is it, right? So you can put in whatever number you want. Maybe it's the 7th root of 26 or something. Who cares? It doesn't matter. The important thing is that you can find the operators. Okay? Hopefully that was helpful. I know some of you don't necessarily know your calculator super well. Okay, now let's move on to D. D is a bit of a tricky one because it deals with numbers and letters. So the important thing you're going to want to remember is that for numbers, you look for the perfect squares, cubes, and so on. And by that I mean those are your factors you're looking for. For variables, or letters, you look for the same thing, but you look for multiples of 2, 3, and 4, etc. What I mean is, if it's a perfect square you're looking for, then you want powers of 2, or 4, or 6. To be more specific, when you're dealing with perfect squares, what it looks like as a variable is your 2s, 4s, 6s, and 8s. If you're looking for perfect cubes, you're looking for your 3s, your 6s, your 9s, your 12s on top of the variables. And for perfect fourths, 4s, 8s, 12s, and so on. Let me show you why that's important. Zoom in on this. For 32, what are your powers of 4, by the way? Your perfect fourths. Where your perfect fourths are, if you want to look in the table this list, 1, 16, and 81 are our first few, okay? 1, 16, 81. That is 1 to the power of 4, 2 to the power of 4, 3 to the power of 4, and you can play that game all day. The important thing is that we notice that we have a perfect fourth. So you can split this up. This can be the fourth power of 16 times 2. That would be our number taken care of, and we'll bring that outside the root after, and we'll be fine. That 16 is going to come out, get a fourth root of it, it gives us a 2, and the 2 will be left inside the root. Now, for the variables, it's a little different, but I did show this in the last class. Because it's a 4, we want to have powers of 4 as our variables. Or the variables should be perfect fourths, or power of 8, power of 12, and so on. So a to the power of 3 stays the way it is. b6, that's actually b to the power of 4 times b to the power of 2. And we've got our power of 4 here. That'll come right outside as a b after. C to the power of 9, same game. Take out a c to the power of 8 and leave 1. Because c to the power of 8 times c is c to the power of 9. So we've sufficiently split it up. So let me be very clear here. This is the exact same thing. These two things are the exact same thing. The reason we did this is now we have so many perfect fourths. I'm going to circle all of them. There's a perfect fourth. Here's a perfect fourth. Here's a perfect fourth, or a multiple of a perfect fourth. we're going to take them outside of the root and fourth root them on the way out. So the fourth root of 16 is 2. The fourth root of b to the power of 4 is just b. Fourth root of c to the power of 8 is c power 2. Think of it as dividing it by the index. So 4 divided by 4 is 1. 8 divided by 4 is 2. And if it was a multiple, for example, if it was a 12, it would be divided by 4 and give a 3 and so on. But that's all we got now. And now we just need to write what's left over in our roots. Okay, so what's left is a 2, an a cubed, and a c. I could probably fix that root a little bit. So a new concept, to be sure, probably something that you're not super familiar with or not very comfortable with, but hopefully not too difficult for you. So I'm going to let you try e on your own, and I'll write out the solution. So pause the video, see if you can figure out what e is going to be, or give it a good shot. Notice that it's your perfect squares you're going to be looking for. So hopefully you give it a good try. 100 is a perfect square in itself. It is 10 times 10. Now you could probably pull out a 25 and then work it through that way, but let's just say you noticed right from the get-go that it was a perfect square. What I would do is I would say I've got 100, I'll work on that after. I've got x to the power of 25. I want multiples of 2 though, so I'll make it into 24 and x. And then my y to the power of 14 is already a multiple of 2, so I'm perfectly fine. As I take them out of the radical, the numbers, by numbers I mean this, the numbers will be square rooted, so the square root of 100 is 10. And then my variables will be divided. Divided by what? Divided by this 2 that I know the square root is made of, really, the index. Divide by the index. 24 divided by 2. That's x to the power of 12. That'll leave this x there and get rid of the other one. Y to the power of 14 taken outside the radical is the same as y to the power of 7. And what's left over is my x. Actually, that's it. It's just the x. So to be crystal clear as I can be, the x to the power of 24, if you square root that, you get x to the power of 12. If you have y to the power of 14, you square root that, it's y to the power of 7. And then your x is left under the root, so it's still root of x. Now, some of you might like to do this a different way. Let me give you an alternate method to solve this question. By the way, this is the final answer, even though it looks a little messy at the moment. Why do all these work? Well, let's just say we had, let's just do a smaller version of the question. 100 x to the power of 24, okay? Students might ask, why the heck does this trick that you're showing us work? Well, you're getting the square root of this, aren't we? So really what we have is the square root of 100 multiplied by the square root of x to the power of 24. And if you think of them as exponents in exponent form, this is 100 to the power of a half, also known as the square root. So we don't really get a lot out of that. The square root of 100, it's just as easy to say a 10, okay? But for exponents and variables, it's very helpful, because x to the power of 24 to the power of 1/2, and let's not forget that this root is the exact same as saying it's to the power of a half. Exponents to the power of exponents multiply. What is 24 times a half? Is the same thing as 24 divided by 2, which is 12. So it's 10 x to the power of 12. All right? That's because 24 times a half is the same thing as 24 divided by 2, which is 12, which is exactly where that 12 comes from, okay? So there's lots of stuff to juggle here. I'm only really scratching the surface of all the different ways you can consider this, but the method that I give you here for these questions is really, I think, the fastest way. So I'm going to do a couple more examples. I'm going to do these 2 examples, okay? I'm not going to talk through it. I'm just going to write out what my answer is, and I hope that that's enough. If that's not enough, feel free to contact me. I'll go through any of the steps, okay? I'm going to go through this without any explanation. So just pause the video, see what you get, and then compare it to my solution after. That's our first one done. Let's try the second one, see how different it is, if different at all. Here we are. Hopefully that matches up with what you tried, and if you didn't try it at all, you're, try to do these, because any one of these questions in this course could be asked on the final exam, okay? So try to keep up, and if you're having trouble, please, this is the time to email me and let me know. I don't mind putting aside some time. Let's move on to page 7. Objective 8.2.2 is to add and subtract radicals, which, believe it or not, we haven't done yet. And it says here, in order to add or subtract radical expressions, which is this kind of stuff, expressions with radicals in them, the radicals must be similar. Or, in other words, it's kind of like, think like terms, where the radical almost acts as a variable, and if they're the same radical, then we can add or subtract them easily. It says here, radicals are similar if they differ only in their numerical coefficients. For example, 5 root 2 and negative 7 root 2. The important thing is exactly what I said before. It's almost like a like term. You can think of this almost like an x. So the tip is to think like terms, and let me show you a little example. If you had 5x minus 7x, what would that be? Should be easy, right? It's 5x's minus 7x's, so you have negative 2x. The radical situation is exactly the same. What if we had 5 root 2 minus 7 root 2? Some students get stumped on that, but don't be afraid of these things. It's just something that's alike. So 5 root 2's minus 7 root 2's is negative 2 root 2's. So there's a huge kind of analogy to be made here. There's a really close connection between these two ideas. If you kind of treat your radicals like almost like they're variables, and if they're the same, you can add them. If they're not the same, you can't add them. You should be fine, okay? So it says here, to add or subtract radicals, express each radical in simplest form, so try to simplify it as much as you can, rationalize them. We'll get to that in a later page, and then we combine similar terms. So let's do some examples, shall we? I'll do the first one for you. Right here, right off the bat, what you should see is that we have root 7, root 7, root 7. We have like terms. 2 minus 5 plus 1. So shouldn't take you very long to get negative 2 root 7 as your answer for this. We'll put it in a nice little box, and we can move on. I'd like you to try the next one yourself. What you should get is 3 fifth root of 6. So try this, pause the video, see if you can get it. How I do this is I notice that I have a like term, a like term, and a like term. So no matter how complicated it looks, I really only need to work with the coefficients. I have 1 of these, 4 of these, take away 2. That's the same thing as 5 minus 2. So 3 fifth root of 6. Let's try C. C is a little different because we actually have 2 different types of radicals. We have root 5's and we have root 3's. That is not a problem. It's the exact same thing as if we had, for example, x's and y's. It isn't an x and a y, but it might as well be. They work exactly the same way. So just group your root 5 terms. You have 1 root 5 minus 5. It's negative 4 root 5. And then your 2 root 3 stays on its own. Nothing can touch it, right? Because there are no like radicals. And there's no way we can simplify it to make it work. All right? Moving on. There's lots more of these. I won't do every single one all the way out, but let's see what we can do. 2 plus root 8. Well, first thing I would do is say, well, root 8 is the exact same thing as the root of 4 times 2, which really is 2 root 2. And in many cases, students like to jump straight from this to that. And your calculator will give you that. So really we have root 2 plus root 8, which is really 2 root 2. And now we see our like terms pop out of this. Root 2 and root 2. 1 root 2 plus 2 root 2 is 3 root 2. So don't let me rush you here. Pause the video at any point if you need to. Make sure that this is making sense to you. And I'm not going to stop saying this. The calculator can really, really, really help. And I really recommend you get the Casio 991 ES Plus. Because this is what it can do. Radical of 2 plus radical of 8, or I should say square root. 3 root 2. How nice is that? Calculator just does it for you. And if this is a multiple choice, why waste your time, right? Why waste your time? So root 24 plus root 54. What the heck are we going to do here? They don't look like there's anything in common, so you might just give up. But don't give up. Root 24, try to find out if you got a perfect square in there. Turns out you do. You got a 4 and a 6. 4 being your perfect square, so that is 2 root 6. What about root 54? Root 54, what do we have in here? We have a 9 times 6, 9 being a perfect square. Take that outside, it's a 3 root 6. Now we got something going on here. What do we have in common? We have a 2 root 6, let me write out the whole thing. You've got a 2 root 6 plus 3 root 6. Many students jump right to this without writing the other work. And now we have our root 6's in common, correct? So we have 5 root 6. Give f a try. And again, pause the video at any point. I'm just trying to go quickly so that we don't make this big long video. F. What are we going to get for f? It looks very complicated, but hopefully once I put this out on the page, you'll make some sense of it. Okay? I'm going to start writing out the solution and see if you get the same thing as me. Root 2 plus 13 root 3. Let's see if the Casio agrees with me. Let me put in the full initial statement. 13 root 3 plus root 2. I've got root 2 plus 13 root 3. Same terms. Order doesn't matter. So I've got the exact same thing. Look how nice that Casio does it. So if this is a multiple choice, it would be foolish not to use the calculator. If it asks for work, though, you got to be able to show the work. That is it for adding and subtracting radicals. The next thing we're going to do is multiply and divide radicals. Multiplying and dividing radicals, in my opinion, is actually easier in a lot of ways than adding and subtracting. It says here to multiply and divide radicals, follow normal procedures for algebraic multiplication, so treat it like they're variables, and division, of course. And the most important thing it says is to multiply or divide radicals, it is necessary that the orders be the same. Orders meaning the index. The index needs to be the same in order for your radical rules to work. So in this first case, we see that our radicals are the same, the index is the same, the order is the same. Group them under one big radical, it's root 10. Following the same rule, try B and C. Pause the video, see if you can get those answers to work out, okay? When I try these, I know that they're the same radical. They multiply together, 99 under a root. The next one, are they the same? Heck yeah, they are. 3 and 3, combine them under one radical. It's the cube root of 24. Not much to that one. The only little extra piece of the puzzle here is to notice that 24 is actually the same as 8 times 3, 8 being a perfect cube. 2 to the power of 3 is 8. So really, I can pull a 2 outside of this. Just like I was doing on the previous page. So these are our first few answers. I'll show you how I would do D. D, if you understand what these brackets mean, is not complicated. You got your brackets, all you need to do is make sure you open the brackets by multiplying through. And let's take it one step at a time. First term times the outside term. This term times this term. It would be our numbers first, so 3, and then it's root 2 times root 5, which is root 10. Do the same thing. It's 1 times a negative 4, which is a negative 4, and then the roots are the same, so you can multiply them. It's root 2 and root 2, which is root 4. You could have skipped that step, actually, and went straight to this. And that would be your final answer. So, by the way, if you had a situation where you have a root 2 times a root 2, which is what happened, root 2 times a root 2 is root of 2 squared, which is exactly 2. So in most cases, you might want to use that as a shortcut. If you've got two of the same roots multiplied together, just forget about the roots. Same situation if you had root 3 times root 3. Just take the number. Or if you had a third root of 7 times a third root of 7, it would still give, actually that's a bad example. Let's keep it at the roots. The square roots are probably the safest way to do it. And they come up a lot, especially in this section. So let's try another question. I'll do E for you. This is 2 root 7 power 2. Probably the easiest way to approach this is to use your regular exponent rules, distribute it inwards. What we'll end up with is 2 to the power of 2, and then we're squaring root 7. The square of a root, or the square of a square root, is just going to cancel the square root. Cancel, cancel. So we're left with 4, 7, 28. We'll do F as well, and then I'll leave a few for you to do. In this case, we have 2 brackets. Pause the video and think about how you're going to approach this problem. I'm going to use FOIL, which is first times the outside times the inside times the last, right? This times this, and this times this, this times this, and this times this. It's kind of how I like to approach these. I don't know, I'm trying to think of a good way to write it, but that's probably as good as I can do. So, let's take it piece by piece, shall we? 3 times 5 is 15. 3 times root 6 is 3 root 6. Negative root 6 times 5 is negative 5 root 6. And then we have root 6 times root 6. Well, I just told you a shortcut for that. You can ignore the roots, it just pops out as 6. And now we simplify. Our constant terms can be grouped, giving us a 21. And our roots, or like terms, I should really just focus on the like term here, but it doesn't really matter. It's a 3 minus 5, that's a negative 2 root 6. So I hope that you see as we go through this, it's not that difficult, it's just can be confusing. And let me double check that I haven't messed anything up. Yes, I had a feeling I messed it up. Maybe you're already yelling at me. What did I mess up? If you pause the video, maybe you can think about it. What did I do wrong? I jumped the gun when I did this. It's negative root 6 and a positive root 6 multiplied together to give this. So negative times a positive, you got it. Those of you that are yelling at me now, I'm really sorry. You got a negative. So it's now 15 minus 6. 15 minus 6 gives a 9. So sorry about that. I made a little mistake there. So I'll put a little star on that. So you can, if you go back to that, know that I made a mistake. Give G a shot here. And I'll write the answer for you so you have something to compare it to. You should get 17 minus 4 root 15. Pause the video, see if you can get that answer. I'm going to go through that question really quickly, and you can see how I plan to do it, or how I would do this question. Just in case you're lost at this step, if you have a root, a power of 2 or a power of 3 and exponent at all on something that has a plus or a minus in between, it's not a product, then we can't distribute. This whole distribution thing can't be done. You have to split it into 2 pieces. You have to multiply it by itself. And then if you do that, you'll be fine. Don't distribute onto each term. You're going to get it wrong in that way. The rest I'm not going to explain. I'm just going to use FOIL again, okay? So I recommend that you check that answer also on the Casio if you have it. If you don't have the Casio, I'm not going to tell you you have to buy it, but I am going to tell you that it would save you a whole lot of effort when you're checking this work, okay? So I recommend you try the Casio. And once again, the name of that calculator is the Casio FX991ES Plus. That's my favorite calculator. You'll use it for this course, obviously, for your next course, Math 1101, and also Math 2100. So just a little piece of advice. Try to find that calculator. You're going to save yourself a lot of trouble. Let's do H and I. H, if you've got, we've already done this actually, if you've got matching radicals, you can divide it one by the other. So you can just say, hey, put the whole thing under the radical because you've got matching radicals. You've got the same index. You can combine them. That was a rule we talked about earlier. And now it's the root of 6 over 3, also known as the root of 2. 6 divided by 3 is 2. And that's actually finished now. There's really no other way to do that question than by doing it that way. For the next question, I'd like you to give it a shot. See if you can get 3 over 4 root 5 for this. So pause the video, see if you can get 3 over 4 root 5. How I do this is I would actually do the terms one at a time. What I mean is I would do your numbers, do that division, and then your radicals do that division. So 6 divided by 8 can simplify down to 3 over 4. 10 divided by 2, if you divide 10 by 2, you're going to get 5. And I'm using the same rule as this, I just skipped a step, but you could think of it as 10 divided by 2, which is root 5, okay? So I'm going to get 5 under that. This is what I end up with. I have a 3 over 4 and a root 5 at the end. And really that's all I can do with that question. So I've said it before and I'll say it again. Don't be afraid to pause the video, take your time, and go back to try these questions yourself, okay? It's very important that you do that. Now, I'm going to push ahead to do the very next page, which is actually the last page of the unit. The other, I guess, 3 pages after that, pages 10, 11, and 12, are all practice. And the reason I'm going to push ahead is that the next topic is very straightforward. There's really not much to it. Really much of the work is in the setup. So objective 8.2.4, and again, this is page 9. It says, well, what we're going to do is simplify expressions containing radicals, including rationalizing the denominator. What does that mean? Well, turns out it actually doesn't mean a whole lot. It's quite simple. Rationalizing the denominator changes the denominator from an irrational, I should highlight all of this actually, rationalizing the denominator changes the denominator from an irrational to a rational number. So it changes it from a radical to kind of a regular number. Or in other words, rationalizing removes radicals from the denominators. And the reason we do that, it's much easier to add and subtract fractions whose denominators do not have radicals. So what I mean by that is you look ahead and you're like, hey, this would end up with a radical on bottom. This has a radical on bottom. We got to rationalize that out. Look at all these radicals on bottom. We want to get rid of those. We want to delete them. We want to cancel them out somehow. And how we cancel them out are by rationalizing. All we do when we rationalize is multiply everything by the denominator. Okay? If it's just a single denominator, we multiply by the denominator only. So let me show you an example. This can be split up into root 2 over root 5 by rules we saw before. We want to multiply everything by the bottom. Multiplying top and bottom by that. And then simplify. What's root 5 times root 5? Well, by our shortcut before, if it's the same root, the root can cancel. It just leaves us with our 5. Final answer, root 10 over 5. Try the next one yourself. Pause the video, see if you can get 5 over 6 root 2. This is how I would do it. I notice that I have a root on bottom. In order to get rid of it, multiplying top and bottom by that root. The top can't simplify. Not yet, anyway. The bottom, root 18 times root 18, deletes that square root. Can we go any further? Well, I would immediately notice, or try to figure out, if 5 over 18 simplifies, which it doesn't. 5 divided by 18 doesn't get us anywhere, but root 18 does. So what I would do is go one step further. I would have the 5. Root 18 is the same as root, let me write this down. Root 18 is the same as root 9 times 2. Take the 9 outside, becomes a 3. You got 3 root 2. So we have times 3 root 2, and the 18 still on the bottom. For those of you that didn't catch what I did, root 18 is 3 root 2. They're the exact same thing. Let's go a little further. We have 5 times 3, so 15 root 2 over 18. And then it turns out that 15 over 18 can simplify, into, I believe, 5 over 6, which is 5 root 2 over 6. So a little bit involved in terms of simplifying this step, and there's many ways to do it. You could have simplified certain things first. Like, for example, some students would see this 3 and 18 and simplify it now. It's up to you. It doesn't matter to me how you proceed, what order you proceed in, as long as you get the final answer okay. And once again, speaking of the final answer, keep in mind that you can go right from the beginning and try to rationalize this. 5 divided by root 18. Let's see what Mr. Cassio has to say. 5 root 2 over 6. What a coincidence! It's not a coincidence, it's math, and the calculator knows how to do it, and you should get the calculator. Have I made myself clear yet? Okay, last topic. We just rationalized denominators that had a single term. The way that we rationalize denominators that are the sum or the difference of two terms, for example, two terms, is to multiply the top and bottom by the difference or sum of the same two terms. What it means is the conjugate. So let's just look at the first example. It's better to learn by example. Notice that this is a minus, so we need to multiply top and bottom by the same thing, but switch the middle sign. Flip the sign. It's called multiplying by the conjugate. So in other words, notice that you have root 3 minus 2. The conjugate is root 3 plus 2. That's the whole point. It starts as a minus and it becomes a plus. If it started as a plus, it would become a minus. So how this plays out now is we've multiplied the whole top by this and the whole bottom times this. We do FOIL if we need to. We open the brackets if we need to. So it's 1 times root 3, which is root 3. 1 times root 2 is root 2. On the bottom, we do FOIL, but it's going to end up being quite easy because we have root 3 times root 3. Use your shortcut for roots. It just pops out the number 3. We have root 3 times root 2 next, which is root 6. We have negative root 2 times root 3 next, which is negative root 6. And finally, we have a negative 2. So take your time to think through that, but I'll try to make it clear for you. Root 3 times root 3 gives a 3. Root 3 times a root 2 gives a root 6. Negative root 2 times a root 3 gives a negative root 6. And negative root 2 times a positive root 2 gives a negative root 2. Let me let you in on a little secret here. By using the conjugate, multiplying by the conjugate always gives us a difference of squares. And why that's important is that we can literally take the first term and square it, and take the second term and square it, and that's what we're going to end up with in the end here. Let me show you that that's true. Try to simplify the top. You can't do it. You end up with root 3 plus root 2. Try to simplify the bottom. You absolutely can cancel things. You have positive root 6 and minus root 6. They cancel out. All you're left with is 3 minus 2, and 3 minus 2 is 1. So this whole thing is over 1. Or to finish the question, we have root 3 plus root 2. We no longer have radicals in the denominator, and all is well. Okay, so what we did, by the way, when you finish this, I said it was difference of squares. 3 squared is 3. That's all that I was left with here. And the root 2, same idea. Root 2, square it, I'm left with a 2. And then they simplify really easily. So I'm actually going to end the video here. I will start the next class by working through the other two examples here, B and C. If you wanted to try these examples on your own before then, see if you can work out the answer to B to be this, and see if you can work out answer C to be this. That's about it. That's what we're going to cover for this video. I hope you learned something. I hope it wasn't too overwhelming. Please keep track of any questions that you have. I'm happy to go through them in class if and when we get time. And if we don't have time in class, I have lots of time for office hours, okay? Especially at this time of the year, near the end of the term. So take care of yourselves, and we will see you next time.